Hi folks, welcome to lesson 2 of vectors. So what we're going to look at now is how we combine vectors. In other words, how do we operate with these new mathematical objects we've defined called vectors, which include both a numerical component, the magnitude, and a direction component. All right, and I've made some references already to how things worked in one dimension. All right, so we talked, remember when we were looking at Broccoli Bear, how we were able to extend describing the motion of Broccoli Bear, okay, which involved moving just left and right, okay, to this idea of moving any direction in 2 dimensions using the idea of a vector. All right, but what we want is we want to make sure that anything we define in 2 dimensions would work when we move back down to 1 dimension. So this is why what we're going to do is start off with what we call one-dimensional vectors as our inspiration for where we go next. All right, so instead of talking about the number 2, what I'm going to do is I'm going to think of the vector 2. In other words, the vector that starts at 0 and ends at 2, and this would be the vector 3. Starts at 0 and ends at 3. Now, you have to think that these are one-dimensional vectors. They lie on the number line here, but just to make it a little clearer, I'll draw them below. All right, so let's start with this idea of scalar multiplication. So if I want to create a vector that is 3 times longer than vector 2, well, what would I do if this was the number 2? I'd multiply it by 3. Well, with vectors, we talked about scalar multiplication. So taking this vector 2 and multiplying it by the number 3 to get the vector 6. So this seems to work out, that the vector 6 is just going to be the result of multiplying vector 2 by the scalar 3. Creates the vector same direction, but 3 times longer. In other words, the vector 6. Okay, so that seems to fit. Let's now talk about addition, because let's say I want to look at the vector 2 plus the vector 3. Well, I know I want my answer to be the vector 5, because remember, we want anything we define in terms of vectors to work with our normal view of numbers. All right, so how can we do this? Well, this is where I can take my vector 3, because remember, vectors are movable, and place it at the tip of vector 2. And if I join them together, look what I get. I get a vector that goes from 0 to 5. And this is how we're going to define vector addition, okay? Is we're going to take the tail of the second vector and place it at the tip of the first vector. And this is what we call tip-to-tail addition. Okay, so again, I start off with vectors 2 and 3. If I want to add 2 and 3, I move vector 3 to the tip of vector 2, and then this new vector from the tail of the first to the tip of the second gives me my vector 5, which of course corresponds to our usual addition of numbers. All right, let's see how we can define this idea of subtraction. Well, let's say I want to take the vector 5 and I want to subtract the vector 2. So here I've got 5, here I've got 2. Well, how did we define addition when we were dealing with just numbers? Well, we defined addition as, how did we define subtraction? Sorry about that. We defined subtraction as adding the negative of the number. So let's see what happens if instead of thinking of 5 minus 2, vector 5 minus vector 2, let's think about adding the opposite of vector 2, which should just be same magnitude in opposite direction. So in other words, adding negative 2. So let me do what I did before, is let me take the tail of the second and place it to the tip of the first, and look what I end up with. If I use my rule from before that the result of this addition is from the tail of the first to the tip of the second, look at what I get. I get the vector 3, which is exactly what we would expect to get when I subtract vectors 5 by vector 2. Okay, so again, we're going to define subtraction as adding the opposite of the second vector. All right, so this gives us a starting point. So now let's see what happens when we move this up to 2 dimensions. All right, so if I've got vectors u and v and I want to add these together, well, let me use the conjecture from before. Let me take my first vector u, and to add vector v, I'm going to place the tail of vector v at the tip of vector u. All right, and remember what we said the sum was going to be, from the tail of the first to the tip of the second. And this is how we are going to define vector addition. Okay, this here represents the sum of the vectors u and v. So it's using the exact same idea as we did in one dimension, is you take the tail of the second, put it to the tip of the first, and the result goes from the tail of the first to the tip of the second, from the tail of the first to the tip of the second. All right? But there's actually another way in which we consider this addition. Because remember, we talked about the angle between two vectors as being given by the angle when they're placed tail to tail. Okay? So here, is there a way to see addition with the vectors placed tail to tail? Well, if you take what we want the resultant to be in that sum, you realize that if I extend these lines here, that the sum of the two vectors is just going to be the diagonal of the parallelogram formed by the two vectors placed tail to tail. And this is our second way of looking at the sum of two vectors. It's the diagonal of the parallelogram from the two tails. All right, so 2 ways of considering vector addition. All right, so let's move this aside. We'll come back to that in a second, but let's now consider subtraction of 2 vectors. Well, we said subtracting 2 vectors was just adding the opposite of the second vector. So if I want to look at u minus v, well, I'm going to take u and I'm going to add to that the opposite of vector v. Okay, in other words, negative v. And how do we add vectors? Well, again, tip to tail. So vector u plus vector negative v, and the result is going to be from the tail of the first to the tip of the second. And so this is one way in which we can do vector subtraction, just by adding the negative. But again, like before, there's a second view of this. I want you to notice that this vector here, if I, which I'm completely allowed to do, move it, and I realize that that represents, hey, look what's going to come back, the old parallelogram. And we realize that the subtraction of the 2 vectors just gives us the other diagonal of the parallelogram, the one that joins the 2 tips. So if I'm looking at vector u minus v, well, it's just, I notice, starting at the tip of the second to the tip of the first. Okay, so from the tip of the second to the tip of the first. But since we're talking about operations on vectors, we might want to ask ourselves, well, what properties do these have? And one property that we always seem to look at when we're looking at addition and subtraction is this commutative? So does the order matter? So let's go back to addition. Okay, well, we know that the sum of the 2 vectors is this vector here, which we found before. Well, hey, we can kind of use the old parallelogram to prove that it is indeed commutative, which again, we hope it is going to be commutative, because I notice that I can do vector u plus vector v using the top half, and look what I get, vector u plus v. Or I could first start with v and then add vector u. And look what I get. I get the exact same resultant vector. So what's really nice about this parallelogram view of things is it in fact proves the commutativity of addition of two vectors, that whether I do u plus v or v plus u, I get the same result. Okay, let's take a look at subtraction. Actually, we'll leave that there. We'll get rid of these here. Now, we already know that u minus v was this vector going from the tip of v to the tip of u. Well, let's do v minus u. So if I do v minus u, which is just going to be v plus negative u, well, from the tail of the first to the tip of the second, there's v minus u. But notice, if I move this along, it's still that diagonal between the two tips, except it is now pointing in the opposite direction, okay? Which kind of makes sense because the pattern we found was that it goes from the tip of the second, which now is u, to the tip of the first, which is now v. So we see that v minus u and u minus v, they're not equal, but as we hoped, they are opposites of each other. All right? So let's take a look at how this all comes together. Okay? Two ways of seeing vector addition, what we call the tip-to-tail method, which is place them tip to tail, and then the resultant, the sum, is from the tail of the first to the tip of the second, or the parallelogram method, where you place them tail to tail, and then the sum is the diagonal starting from the two tails. Vector subtraction can just be seen as adding the negative or opposite of the vector, or it can also be seen within the parallelogram method as being the diagonal joining the two tips. But notice how it goes from the tip of the second to the tip of the first. So if I was doing v minus u, it would just be going in the opposite direction. So now we're also seeing some properties of these operations. Addition is commutative, subtraction is not, but if you change the order, it does give you the opposite vector. Okay, so see the next video for a couple of examples on how we actually add vectors using numbers.